So let's practice this proofreading thought process, these habits of mind we're trying to develop. Let's practice these by reading an actual proof, and I'll walk you through kind of the way that I think as I read this. So first, since we're going to give a definition, we're going to do a proof about square roots. First, I've included a precise definition of what we mean when we say square root, so I'm going to read that first. The definition is suppose S is a non-negative real number. So when I read this, my brain is converting this to the assumption. This means S is in the reals, and non-negative means that S is greater than or equal to 0. So S can be 0, but it's certainly not negative. Okay, so that's the setup. Then the definition says we say that R is the square root of S. So notice that square root is italicized to tell you this is the word we're defining. We say that R is the square root of S and write R equals square root of S. So this is defining the symbol square root of S. If R is a non-negative real and R squared equals S. So this corresponds to our intuition of what we think square roots are. R is the square root of S if R squared equals S. But if we're going to prove things about square roots, we have to be very precise and write down a definition so that if you had never heard the word square root before or seen this symbol before, you would be able to manipulate it in a proof and rigorously show its properties. So now we're going to prove something about square roots, and we're really only allowed to use this definition. We can't use any of our other knowledge about square roots because we haven't proven them. Okay, so let's read the theorem, and remember that our checklist when reading a theorem is to ask what are the assumptions, what is the conclusion, and do I understand the definitions of all of the words. So, theorem, if S is a non-negative real number, so this is signaled by the if, this is our assumption. We're assuming that S is a non-negative real number, that's our assumption, then that signals the conclusion, square root of S is unique. So here's the conclusion. And now we ask, do we understand all of the words mathematically that are being used in this sentence? So the word unique in a mathematical context means that there is only one number with that property. You cannot have two distinct numbers that satisfy the definition of the square root of S. So we understand unique. Do we understand what square root of S means? Well, yes, that's this definition here. So the square root of S means it is a number such that the square of that number equals S. Good. So I think we understand the assumption and the conclusion, and now our brain is primed, because now that we know what the assumption and conclusion are, we expect the proof to have the form assume assumption, then some deduction, then some other deduction, and a flow that eventually leads to the conclusion. So now we see that coming. Okay, so let's begin reading the proof. So the first sentence, as we expected, says let S be a non-negative real number. So this is restating our assumption, but it's also setting notation. What do I mean by that? I mean that in addition to telling us that we're starting with this non-negative real number, this is declaring a variable S, right? So this is just like if you're programming in a language like C++, where you have to say something. You declare a variable by saying int a. You don't have to do that in Python, but you do it in statically typed languages. So if I say int a, this is telling the compiler, look, I'm going to use this variable a, and I'm telling you a property about the variable that it's an integer. So you know what integers are, compiler. That means you know how to handle this variable. When we write a proof, before you speak about any number or set, you need to declare it and tell the reader what it is, right? So that's what we're doing in this first sentence. We declare this S, and we tell the reader it's a non-negative real number. Okay. So now we move on to the next sentence. To show uniqueness, so this is just guidance text, we're not deducing anything here. To show uniqueness, now suppose two numbers R and R tilde satisfy the definition of square root S. So this is another assumption. We're making an assumption in this sentence, and we're actually, in that assumption, declaring two variables. So we're declaring one variable R, which we say satisfies kind of the definition of square root of S, and then we do the same thing with this declare R tilde, which is a second variable that also satisfies the definition of square root of S. So why did we declare two variables that satisfy the same definition? Because we're trying to show that the square root of S is unique, so there can only be one. And a uniqueness proof typically proceeds by, okay, to show there's only one, I'm going to instead suppose there's two of them and prove that those two must be equal. It follows that if any time there are two, they must be equal. This means there is, in fact, only one of them. Right. Okay, so we've just declared two variables, R and R tilde. They're both square roots of S. Okay, so then what is going on in this next sentence? This means that. Okay, so we know that when you see this means that, this is going to be a deduction. This is something else which must be true given what we've said so far. So this is a deduction, and what are we deducing? We deduce that r is non-negative, r tilde is non-negative, and r squared equals s equals r tilde squared. Okay, so I've said whenever you read a deduction, you should ask why is that true? So why do we know that both of these numbers are non-negative and they square to s? Well, how do we know that? All we know about r and r tilde is that we've assumed that they satisfy the definition of square root of s. So I go back up and look at that definition. We say r is the square root of s if it's non-negative and it squares to s. Aha, okay. So that's how we know this is true, because we've assumed they satisfy a definition, and that definition says they're non-negative, which means greater than or equal to 0, and it means they square to s, which we've said here. So this sentence deduces that these two numbers have the properties stated in the definition of a square root. So this is deduction from the definition of square root, from def of square root. Okay, so I think we understand that sentence. Move on to the next sentence. We need to show that r equals r tilde. Okay, that's not a deduction. That's just guidance text. You're signaling to the reader what you're going to do next, because it's a uniqueness proof, so we're trying to show the two things are equal. Okay, so we don't need to think too hard about that sentence because it's just guidance. Next sentence. Since r squared equals r tilde squared, how did we know that was true? Okay, that's this conclusion, so we already know that's true from 2 sentences ago. Since r squared equals r tilde squared, that means we're going to have another deduction, so this is another deduction, and the deduction is this equation. 0 equals r squared minus r tilde squared. Well, how do we know this is true? That's just taking the equation we had, that they're equal, and subtracting r tilde squared from both sides, right? So we took this equation and subtracted r tilde squared from both sides. Good. How do we know this is true? Well, this is factoring. So they're equal because we just factored a difference of two squares, right? R squared minus r tilde squared is the product, r minus r tilde, r plus r tilde. Okay, so I think we understand why that deduction is true. It was just moving something to the other side and then factoring. Next sentence. Thus, when we see thus, we know that means it's a deduction, so this is a deduction. Deduction. Either r minus r tilde equals 0 or r plus r tilde equals 0. How did we know this is true? Well, this is the zero product rule, right? If the product of two numbers is 0, then one of those two numbers must be 0, right? So we knew from the previous equation that the product of these two numbers is 0, so we use the zero product rule to say there are two cases. Either the first one is 0 or the second one is 0. So when you get to an or statement in a proof, that normally means you need to handle both cases in the or separately, right? Because P or Q is true when either P is true or Q is true, or possibly both. So whenever we have an or, we have to split into cases. Okay. So here's the first case. If r minus r tilde equals 0, okay, so this is the first case, case 1. The first one is 0. If r minus r tilde is 0, then r equals r tilde, and we are done. What does that mean? Well, this is what we wanted to prove, right? We were trying to prove uniqueness, which means if there are two square roots, r and r tilde, they must be equal. So in the first case, we have proved they're equal, so that concludes that branch of the proof in that or, that case of the or. Okay, so then we just have to go back and handle the other case. Okay, so here's case 2 coming. Case 2. If r plus r tilde equals 0, then r equals minus r tilde. It's a deduction just by algebra. But now we showed up here, we deduced before that both of these numbers are non-negative. So the only way you can have two numbers that are equal, that are opposites, one is minus the other. The only way you can have two numbers that are opposites but are both non-negative is if both of them is 0, right? If one were positive, then the other would be negative, which contradicts our previous assumption. So in this case 2, the only possibility, this deduction, is that r must be 0, which means r tilde is also 0, and again they're equal. So that was this deduction by if r equals minus r tilde and they're both non-negative, the only possibility is they're both 0, which means we again have shown r equals r tilde. Okay, so that's case 2. So now we conclude, this is the conclusion we were trying to show, because we showed there were two cases, either r equals r tilde or r equals minus r tilde. In both of those cases, it's actually true that r equals r tilde, which is what we were trying to prove all along. So then we state the conclusion. Thus it holds generally that r equals r tilde, and we put a box. Good. So that's how to read a proof. It takes a long time. You have to read each sentence probably multiple times. You have to kind of refer back. You don't read linearly, where you just, like reading a book, you read one sentence, then the next sentence. That doesn't work with proofs. You have to read one sentence, go back up, look at the definition, scribble on the side, try to read the next sentence, get confused, go back, possibly write some notes in the margins. But as long as you start by asking what are the assumptions, conclusion, and definitions, and while reading the proof, ask yourself every time there's a deduction, why is this true? And don't continue reading the proof until you know the answer. As long as you follow those steps, it might take a while, but you will eventually understand the proof, and reading enough proofs and understanding them will get you to the point that you can write them fluently.